Hey folks, Thea here, and in this example video, we will locate the pseudo-foci of the elongated circle, aka the ellipse. An ellipse is, like I said, a stretched circle, but also a conic section whose shape is determined by its two real foci. These foci are not to be conflated with its pseudo-foci, which you may know are farther from the curve compared to the real foci. This fact is explained in episode 12, where the ellipse is treated as two functions of which its PFs are found. However, in this video, the ellipse is not as complicated as a parameter compared to a function. In any shape or size, the general ellipse is defined as the parameter a cosine t, b sine t, where a is the horizontal radius and b the vertical radius. Since this is the general ellipse in parametric form, we are finding its PFs differently and more in depth compared to the arbitrary function form of episode 12, which just spoon feeds you the pseudo-foci. To locate the pseudo-foci of an ellipse, we can utilize a three-step rule that we derived last episode, which is generally tedious, but the most precise and straight-to-your-face method to locate them. But I emphasize on tedious, dear viewer, because there's obviously a lot of algebra involved in solving this problem. I encourage that you either skip those parts or grab a piece of paper and do the PFs yourself given this parameter using this method and play this after as your answer key. Without further ado, let us begin. So one way for me to be time efficient with this problem and this video simultaneously is to express cosine and sine in shorthand terms where cosine t is just c and sine t is just s. And whenever I encounter an identity in shorthand such as s squared plus c squared, I know it's gonna be 1. With that, I rewrite the ellipse's parameter to acbs, and boom, shortened. With our shorthand parameter, let us separate each component where x equals ac and y equals bs. These components are then the expression which we differentiate 3 times for step 1. As far as I'm concerned, we are taking the derivative with respect to t here, meaning the shorthand c and s pack a t in them, while a and b are just plain constants which barely change upon differentiation. Speaking of, let's handle the first 3 derivatives of x equals ac. The derivative of ac, or a cosine t, is a times negative sine t, or to rewrite, negative as. Next, we differentiate negative as, or negative a sine t. This one turns into negative a times cosine t, or to rewrite, negative ac. For the third, we take the derivative of that, where negative ac, or negative a cosine t, turns into a sine t, or as. Next, we turn our heads to the y component, y equals bullshit. I hope you are used to differentiating the shorthand terms, so without unpacking them, the bs turns into bc, which is first derivative. After that, we differentiate bc again, where it turns into negative bs. This negative bs undergoes another differentiation, where this time it's negative bc. And these are our derivatives of x and y up to the third derivative in shorthand terms. You know what comes after step 1? The step next to it, which I think is step 2. This is the step where we compile all our primes into a giant equation, which is, in shorthand, x prime, y prime prime prime, minus y prime x prime prime prime, times x prime squared plus y prime squared equals 3 times x prime prime plus y prime prime times x prime y double prime minus y prime x double prime. I should remind you what this equation means. What this equation does is find some value or values of t where the oscillating circle along the parameter reaches its minimum radius. It is also where the evolute of its parameter makes a sudden abrupt turn in its shape, making a cusp. And where these cusps happen is determined by this equation here, which we are going to solve. Since what we're solving is a representation of absurdity, let's cue the momentous music. One strategy to keep my brain cogs turning is to work on plugging the primes factor by factor, where I may rewrite this as f1, f2, 3f3, f4. With that shortened, let's first work with f1, which is x prime y triple prime minus y prime x triple prime. Plugging the primes, x prime becomes negative as, y triple prime becomes negative bc, y prime becomes bc, and x triple prime becomes as. Going further, let's simplify this factor. Multiplying each term, we get asbc minus asbc. Would you look at that? Our f1 actually turns out to be 0. If we look at the equation, f1 multiplies with f2, so f2 just cancels to 0 along with f1, meaning we don't have to work with f2. So we skip to f3, where f3 is the expression x prime prime plus y prime prime. Plugging the primes, x prime becomes negative as, x prime prime becomes negative ac, but then y prime becomes bc, and y double prime becomes negative bs. Now we simplify this factor. Again, multiplying each term, we get a squared sc plus negative b squared sc. Next, we factor an sc here, yielding sc times a squared minus b squared. We can keep going and convert sc to an identity, but we'll do that later. So let's move on to f4, where f4 is the expression x prime y double prime minus y prime x double prime. Like before, we plug the primes where x prime becomes negative as, y double prime becomes negative bs, y prime becomes bc, and x double prime becomes negative ac. By multiplication, we get abs squared minus negative abc squared, or abs squared plus abc squared. You can see we can factor in ab here, so doing so gives us ab times s squared plus c squared. We know that s squared plus c squared is 1, so basically multiplying that times the identity is the same as just ab. And this is our f4 in the equation. With our f3 and f4, we compile them and equal them to the 0 which the f1 and f2 left behind. This makes 0 equals sc times a squared plus b squared times ab. Alright, there are two most apparent simplifications we can do here. Those two are sacrificing the a squared plus b squared in ab to the beast of nothing. Doing so just leaves us with sc equals 0. And earlier, I pledged to convert sc to an identity, so here you go. Sine 2t over 2. But do we really need that half right there? Get out of here. Join the constants. And thus we have sine 2t equals 0, which is a solution of transcendentality. By that I mean we have infinite solutions to this equation. However, we're only concerned about solutions of one revolution of an ellipse, which range values from 0 to 2 pi. What that means, in the context of this equation, is that we draw sine 2t and find when this wave hits 0, but strictly in the domain of 0 to 2 pi. Where the wave hits 0 are finally the values of 0, pi over 2, pi, 3 pi over 2, and 2 pi. But cross out 2 pi because it's just 0 in another revolution. And these are the 4 values that make the original step 2 equation true. And to remind you, these are the 4 values that yield a minimum radius or evolute cusp of the ellipse. And you know what having 4 values imply? 4 pseudo-foci, because we'll have 4 edges on our evolute. And say, we haven't seen the evolute of the ellipse in this video, huh? Well, this takes us to step 3 of the method, where we plug each of the 4 values we have in the evolute parameter. This parameter in shorthand terms is written as the coordinate xy plus x prime squared plus y prime squared all over x prime y double prime minus y prime x double prime times the coordinate negative y prime x prime. Using this parameter, we can first plug the x and y's, then plug the certain value. Working with our primes and original components, the evolute parameter is written as xy, which is acbs, plus x prime squared plus y prime squared, which is negative as squared plus bc squared, all over x prime y prime prime minus y prime x prime, which is negative as times negative es minus bc times negative ac, times the coordinate negative y prime x prime, which is the coordinate negative bc negative as. After that, let's distribute the numerator squares. Then the multiplication in the denominator. After that, the denominator factors in ab, where the inner factor is the identity s squared plus c squared. Of course, this just leaves ab for the den. Out loud, the parameter is written as acbs plus a squared s squared plus b squared c squared all over ab times the coordinate negative bc negative as. And so, we have our ellipse evolute. With our parameter more specific, we can more directly graph this parameter, where this evolute, to some people's surprise, is the asteroid. Let's investigate this for a bit. Since we had 4 solution values from step 2, it makes sense that the pseudo-foci are the 4 cusps or edges of the asteroid. Another important characteristic of the asteroid is that it is symmetric with respect to the x and y axis. So what this implies is that if we have located the PF of the right side, we can also locate the PF of the left side by assumption of symmetry. The same goes with the PF at north to locate the PF of the south. In short, we just have to locate the right PF and the upper PF. But how do we know which PF corresponds to which value? Simple. It's just like how we process the unit circle. This PF on the left here is where the circle starts, so this is where t equals 0. And then this PF up high is where the circle angle is pi over 2, so t equals pi over 2. Thus, let's begin plugging in the c's and s's. To start, when t equals 0, cosine t or c is 1, and sine t or s is 0. So substituting each c and s, our whole parameter ends up with a times 1, 0 times b, plus 0 times a squared plus 1 times b squared all over ab times the coordinate negative b times 1, negative a times 0. Getting that weird binary out, we get a0 plus b squared over ab times the coordinate negative b, 0. Last touch, we reduce the fraction to be a. And this then will be our right pseudo-focus of the ellipse. We then infer that the left pseudo-focus is the negative x of the right PF, so we simply flip the x coordinates, giving us negative a0 plus b over a times b0. Then we take care of the PF on t equals pi over 2. This is the angle where c or cosine t is 0 and s or sine t is 1. Substituting each c and s, our whole parameter ends up with a times 0, b times 1, plus a squared times 1, plus b squared times 0 all over ab times negative b times 0, negative a times 1. This thing then simplifies to 0b plus a over b times 0, negative a. This here is the coordinates of our north PF, so using symmetry, we can acquire the south PF by flipping the signs of the y coordinates where we have 0 negative b plus a over b 0a. With a sigh of relief and a brim of excitement, we have found the 4 pseudo-foci of the general ellipse. So the significance of these points is that first, you draw an osculating circle that centers on the PF and touches a point on the curve. To add, I forgot to mention amidst this series that this point that is kissed by the circle is actually called the vertex, and to restate, the vertex is the point the osculating circle touches when its center is a pseudo-focus. So whenever the circle centers the PF and simultaneously touches the vertex, the osculating circle reaches its minimum radius. And that's the part where I'm half incorrect. Watch as the circle swims along its evolute. See what I could have missed. As you can see here on this horizontal ellipse, the right and left PF are the points when they correspond to the vertex of the respective sides, and when the osculating circle is at minimum. However, the north and south are points when they correspond to the vertex opposite their respective sides and when the osculating circle is at a maximum. So it turns out, the osculating circle not only reaches a minimum radius when it centers on the PF, it is also the maximum radius of the circle, or to sum it out, an extrema value of the radius. To the ellipse's evolute, there are 2 instances of minimum and 2 instances of maximum radii, and it kinda makes sense because the circle has to grow big and shrink small again, given that the ellipse or the evolute are enclosed shapes. And that was a half mistake I made last episode, which I wanted to set right here. And this wraps up for this first parametric pseudo-focus example, and I admit, this episode is stunningly long, and I think I lost some brain cells along the way when editing this video in long sessions. Just kidding, I take regular resting times. I get used to this every day and week. But other than that, if you were confused or did not catch up somewhere in this video, I can help you with that. There's a Desmos link in the description below where I detail each step and the following algebra there. With that out of the way, TYSM so much for watching and tune in for the next example video.